Hello everyone. Today we would like to talk about one device that's used for autonomous vehicle. The device I already mentioned in the common future topics. I think I should talk a little bit about this device. If you already know about this device, fine, but I want to give you the basic knowledge about this device. And every time people talk about radar, you understand basically how it works, right? So the radar is used very popular for the aircraft field. They usually take another aircraft or used for military. Okay, so right now they are increasingly being used for automotive radar sensor for advanced driver assistance system (ADAS). So look at the image right here. You can see in the car right now they use a lot of sensors. And radar is used for adaptive cruise control, or they used for the cross traffic alert or blind spot detection or rear collision warning. Right? The advancement of the radar technology and digital signal processing makes it possible to design efficient radar at a low cost and in smaller size. The radar capability to determine the targets at long range with accurate velocity and spatial information makes it important sensor for self-driving. Not only that, it's able to send objects in the dark, poor weather like rain, false condition. Yeah, it's better than a lidar or the camera. So here's a picture. You can see the radar used for the autonomous vehicle from level 1 to level 5. In the next time, level 4, level 5, so they use a lot of radar in the form autonomous vehicle to object detection, object recognition. The principle of the radar, it means transmitter and receiver. Transmitter right here, they transmit the electromagnetic wave, and they send the signal electromagnetic wave, and they hit to the object. From the object, they get back the reflect the wave back, okay, and receiver to get the signal back right here. From that, they can calculation the distance, how far from radar to the object. Right here in the car, they put the radar in front of the grill right here, and they measure the distance from the object, right? In front of the car. So how the radar used for the car look like? Right here, I show you the box or radar. The bus radar, they have they have radar dome, and they have the radar's printed circuit board, and they have digital processing signal board right here. Okay, and the automotive radar is very small sensor that can easily fit pin it in front of the grill of all the bumpers. So the radar dome right here, the radar dome, it looks like it's a weatherproof enclosure that protects the radar antenna. The radar dome, they construct of material that minimally attenuates the electromagnetic signal transmitted and received by the antenna, effectively transparent to the radar waves. The radar printed circuit board is analog hardware that includes the radar transceiver and antenna needed for radio wave generation. And the last one, circuit board processing, that's the digital signal processing, is the board for process the signal. So the light, as you know, the LiDAR can generate the high resolution image by on the reflection of the laser light from the targets. But the LiDARs fail in the bad weather condition. Its very small wavelength doesn't allow to work well in the frost or rain. Additionally, LiDAR is inexpensive sensor with cost vary from $35,000 to $100,000. Okay, LiDAR is free for technology as the Waymaker, but radar radar lack of the capability to generate high resolution image, but is highly accurate velocity estimation based on the Doppler phenomenon, which we'll cover in more detail later in this course. So, radar's wavelength allow it to send a target in the best weather. Remember the best weather condition. Most importantly, the low manufacturing cost of a radar. A radar unit costs as low as a few $100s. Allow the car manufacturer deploy multiple radar sensors for 360-degree perception. You know, Tesla car, they don't like to use LiDAR. It's so expensive, right? Tesla rely on radar as its primary sensor and doesn't include LiDAR in its sensor fusion system. Here in the picture, you can compare the LiDAR and radar. So, for example, but radar, they have benefit to detect the speed, okay, better than the LiDAR. About the cars LiDAR is better, right? About the work in the snow, frost, rains is better than LiDAR, okay? Resolution is lower, but the LiDAR is better resolution, okay? Here is some the benefits radar and LiDAR. So which one is true? Answer this question. For LiDAR is more reliable sensor than a radar while driving on rainy day. What do you think? Is wrong, right? For the low price car or car manufacturer would prefer install radars rather than LiDAR. Yeah, it's true. Radar is better sensor in estimate the time taken by oncoming car to reach the ego vehicle. It's true, right? And radar is better sensor outlining the object. No, that's some the quiz question. So here I want to show you the basic knowledge in the physics used for the radar. I hope you understand here in the physics class. The wavelength is the physical length from the one point of the wave to the same point on the next wave. This is, for example, the wavelength right here, from here to here. The short wavelength from here is greater with low wavelength. Here you can know it's low frequency, it's the high frequency, right? Wavelength is the ratio between the speed of the light and frequency. And one definition, the frequency of the wave is the number of the wave that's passed by each second, right? It's measured in hertz. In automotive radar, generally operate in the band 76 GHz and 81 GHz. The signal as frequency is referred to millimeter wave since the wavelength is in a millimeter. So the bandwidth of the signal is the differences between the highest and lowest frequency component in continuous band of frequencies. The amplitude, the strength of the signal, right? So it's quite easy. Let's go in physics. How about the phase of the signal? The phase particular point in time of cycle of the waveform measured as angle of degrees. A complete cycle is 360. The phase is an argument value related to start of the cycle. In gradient from 0 to 2 pi. So frequency define the first derivatives of the phase respect to time, right? And phi right here the phase of the signal. Property is measure Doppler frequency shift of moving the target. Right here you can see if the oscillating sine wave right here. And the difference between the phase of two periodic signal is called the phase differences. At the values of when the difference is 0, the two signals are said to be in the phase. Otherwise, they are out of phase with each other. The phase right, the phase information processing important as we go through Doppler processing. Right here, the first and second phase right here. The difference is 90 degree, right? And general equation of the wave, that's a equation right here. A is mean amplitude of the signal, cosine 2 pi. Fc is mean the signal frequency, and theta is the phase of signal. Here are the basics, the school physics. Go back to the signal used for the radar. On the car, we will use the FMCW radar. It means frequency modulated continuous wave radar, especially special type of radar sensor which radiates continuous transmission power. FMCW radar ability to measure very small range to the targets, as well as the ability to measure simultaneously the target's range and its relative velocity. Man is the first choice type of radar for automotive application. Here, so FMCW radar is the popular radar used for automotive application, and the waveforms right here they use the frequency modulated continuous wave is the signal with frequency increasing or decreasing with the time, and they also refers the up ramp or down ramp. So the two most common waveform patterns used for FM's CW radars are the sawtooth or triangular. Okay, the sawtooth right here, you guys, waveform generally use thus the up ramps, whereas the triangular waveform use both up ramp and down ramps. So each chirp right here defined by its slope. Then the slope given by the chirp frequently bandwidth B right here. Okay, the bandwidth you see, and B or the B's width from start smallest one to the highest frequency. Okay, and the term TS right here from here to here. Okay, here the slope it means the ratio between the bandwidth and the chirp terms. Okay. So here's the principle of the radar. They have the frequency synthesizers, the frequency. So frequency generator or the chirp generator, they will generate one frequency, okay, waveform, okay, and after that they go to the power amp right here. The signal will it needs the higher power to reach the target. They're increasing the frequency, right? The frequency generator or the chip generators here, there is a component generate frequency to bring the chirp frequency all the way to 77 gigahertz in case of the automated radar. And go to the power amp right here. Power amp helps amplify the transmit signal. And go to the antenna. Antenna converts the electrical energy into electromagnetic waves, which radiates through the air, hit to the target, and get reflect back toward the radar receiver antenna. They hit to the targets right here. They get back to the receiver antenna right here. The antenna also increasing the strength of the signal by focusing the energy in the desired direction. The antenna patterns determine the field of the radar. So right here, that's amplify the receive the signal, and they go to the mixer. Mixer is used here as the subtractors of transmit frequency from receive frequency. So the mixer the mixer multiply the return signal with the sweeping signal generated by the frequency synthesizer. So the operation works as the frequency subtraction to give frequency delta, also known as the frequency shift. It means the IF right here, the intermediate frequency IF, equal the synthesizer frequency minus return signal frequency. And the last one is processor right here. Here's where the signal processing happen, includes of the tracking, clustering, etc. Right? Detection, blah blah blah. So the antenna, is the transducer that converts electrical energy into electromagnetic waves. In the case of radar, this wave travels through the air and hit to the target, depending on the surface, type, and shape of the target. So the waves get partially reflected back in the direction of the radar. The receiver antennas at the radar amplify the received signal, further send it to the receiver chain for further processing. Here the pattern of the radar. The antenna patterns is a geometric pattern of the strain of related the field emitted by the antenna. So I say again, you have the generator, right? The chip generator or frequency generator. You generate the waves and you go to the power to amplify the transmit signal, and from you go to the antenna right here. They convert electrical into the electromagnetic wave, so electrical energy into the electromagnetic waves, and they send to the object right, hit to the object right here. Object reflect back to the receive antenna right here. Receive antenna right here. They have amplify the receive signal right here. They go to the mixture right here. They got the intermediate is the frequency IF right here, and they go to the analog to digital converter, and the last one they go to the processor, okay, to process the signal for tracking, clustering, something like that. So the right here they have the definition. The beam width of the antenna is determine the field of the view of the radar sensor right here. The antenna beam width. So if the requirement for the radar is to thus send the target in its own lane, then the beam width need to be small enough to cover the completely lane up to desired range. So if the beam width is wider than the lane width, so it will send the target in all the lanes as well. I mean the beam width right here have small enough to cover completely lane right here, okay? And the antenna radiation not only comprise of the main beam, but also they have the side lobes right here. The side lobe right here is critical because they can generate the false alarms and pick interference from the undesired direction. The side lobe of antenna points in different directions and can send targets or not in the main beam. To avoid side lobe detection, it is critical to separate the side lobe level to more than 30 decibel from the bit to the main beam. About the antenna types, so there are too many type antenna dipole patch horn, and that can be used 77 GHz. So most of the more commonly used antenna type automatic radar is the batch antenna. The low cost, easy fabrication, and the low profile patch array antenna the ideal choice for autonomous radar application. So the quick question is, which flowing is true for radar antenna? Strong silent have to avoid interfere. Oh, it's wrong, right? It's really critical and give a lot of for alarm. So, and a strongman beam is used for long range radar. Yeah, it's true right here. Strongman's beam right here. A narrow beam is used for corridor field length, right? And okay, one important thing for the radar right here is the RCS. The radar cross section, okay, the size and ability of the target to reflect the radar energy is defined by a single term, sigma right here, as the radar cross section. So the unit, so that's radar cross section is area. The target's radar cross section area depends on the target's physical geometry, exterior features. So smooth edge or surface would scatter the waves in all directions, hence lower RCS, whereas the sharp corners will focus the return signal back in the direction of the shock, leading to higher RCS. So the direction of the illuminating radar, the radar transmitter frequency, and the material used for the car, truck, bicycle, even some case. You see the radar they put in the front of the grill of the car right here. They generate the signal and they reflect back. So the RCS impact to the signal return to the radar. You look at the picture right here, you can see right signal are send it and they hit to the RCS. It means the area of the back of the car right here and reflect back to the signal. It depends on the area right here. It's influence to the signal strength. Okay, right here you can see in some practice some energy is observed and reflected energy is not distributed equally in all directions. Therefore, the radar cross section is quite difficult to estimate and is normally determined by the measurement. For example, is sphere surface. You can right here. You can the reflect signal is scatters around the surface, but right in the corner they focus to reflect back to the radar. So the RCS can be defined logarithmic value. So because it's increasing the return signal strength, this formula. You can look at the table right here. You can see the target, the main, burst, cabinet, different the RCS. So they have different the area right here and the different the RCS value. You see the higher the cross section, this the higher RCS. And one example, really interesting example for aircraft. This aircraft, how they can avoid the radar detection because the design different, really special design, right? What made the steel aircraft to go undetected by the radars? Because the aircraft smooth surface, second the non-reflective bands, and the last the geometry of the aircraft, thus help the aircraft go undetected by the radars. And the one more thing I mentioned right here is the range equation. Here's the range equation. They had the right here. They had the PS right here transmits the power. G is the gain of transmit and receive antenna. Lambda here's wavelength of signal. Sigma is the RCS radar cross section, and PE is the minimum receive power radar can detect. Okay, a long range radar designed to cover 300 meters range and detect the targets with smaller cross-section would need a higher transmitting power and more antenna gains as compared to short-range radar designed to cover thus 50 similar targets. So a target with a high cross-section can be detected as long range as compared to the target with smaller cross-section. Right here, you look at the signal propagation state right here. The signals powered S level. They transmit this and they go back to transmit chain gain and transmit the antenna gain and go to the RCA gain and return. And right here, the last one they resist right here. Okay. The image shows the variation of signal strength level as it travels through transmitter over the air and as receiver. So the transmitter power right here, the power amplifier, the further increase in the signal strength, right? The signal is further amplified using antenna. So the one-way path loss presents the loss of signal strength as it travels towards the target, and one getting reflect from the target to the signal gets amplified based on the RCS targets. After the RCS gain, the signal bus travel back towards the radar and has similar loss strength as going to forward. The receiver antenna amplifies the return signal before sending to processing units. So here's the first introduction. Next video we'll continue to talk about the radar.